Guess I should be live at some stage. What's the microphone gains doing? Okay, we should be live at some stage. Okay, do we need the camera? If anyone asks for a camera, we can turn it on. Don't mind it. Otherwise, we might just save some electricity. What's up with the gain? No, the gain should be fine. If we're going halfway volume on the stream monitoring. Yeah, that's okay. Guess I'll just start talking to myself, then we talk to a bot. We don't mind talking to a human if you want to come on live in the chat or some other way. We have a bunch of tools on the website, go check them out. A lot of it is deployed. Some of it is still in the making. I'll touch on quite a few things. This is an example of one of them. Yeah, you kind of need to adjust your, so depending on the screen size, it's probably in browsers, is that yes, it works pretty well most of the time, but depending on your screen size, it might appear differently. So you have to like either, well, change the screen or adjust the zoom on in the browser. In this case, yeah, it could be improved quite a bit in terms of how it adjusting itself to the size of the screen. Yes, something like this. Yeah, this one needs a bigger screen size. These things could have an option to remove the labels and things. See how we go. We have this weird screen anyway. Yeah, go check it out. Let me know how it looks like on your screen. Be good to know. Now this will be a random Friday, so we'll be looking at running local models in so we are in Visual Studio Code. We'll be probably using this root code, which is let's say it's a whole team of AI agent in your editor, which is, yeah, okay, fine. But then we might be using it with local models. And we might be reviewing a bunch of papers. And we were turning these papers into web applications. And that's what we are testing the models for. Sorry, so say it again. So essentially take videos or papers, turn them into interactive web applications that you can play with. So instead of reading text like this, it doesn't make any sense. It's funny, I actually talked to the author, said something like this needs to be translated into English. And they're like, what? This is English. But then, no, it is not English. If you get a bunch of equation, I couldn't even pass the abstract of the paper. I couldn't understand does anyone knows what's extrema is? What's extrema? So I might Yeah, this will be pretty random. Happy to answer any questions. And let's actually try a co-host. Well, because there's no human available. If there would be a human, we'll be using a human, but there's no human, so we'll be using AI. So I'll try Google AI Studio using Gemini 2.5 Flash Live Preview, and I'll try that one. We'll share the screen with it for a sec. Let's actually start with something it surely knows a lot about. It's AI models. Okay, do you know how to run? What's root code? Just in one sentence, what's root code where my mouse pointer is?
Root code supports running language models locally on your own machine using Ollama and LM Studio.
Okay, you just read it from the page, did you?
Yes, I did. Is there anything else I can help you with?
Yeah, sure. So what's the difference between these two models?
The two models mentioned are Ollama and LM Studio. Both are used by root code to support running language models locally on your machine. The document does not elaborate on the specific differences between Ollama and LM Studio.
I scroll down a bit. Can you review?
Certainly, the drawbacks of using local models include resource requirements, setup complexity, model performance, and limited features.
So if we do have a GPU, but we are using the GPU for other things as well. We don't have a dedicated GPU to run the model. Can we still run a local model?
The text states that local models are resource intensive, requiring a good CPU and ideally a dedicated GPU. While it's implied that a dedicated GPU would be beneficial, it doesn't explicitly say that you cannot run a local model without one.
Okay, and what's the difference between the two models?
Ollama is described as a popular open source tool for running large language models locally, supporting a wide range of models. LM Studio is a user-friendly desktop application that simplifies the process of downloading, configuring, and running local models, and it also provides a local server that emulates the OpenAI API.
Okay, I scroll down the page a bit.
I see that both Ollama and LM Studio offer similar capabilities, but with different user interfaces and workflows. Ollama provides more control through its command line interface, while LM Studio offers a more user-friendly graphical interface. Is there anything specific you would like to know about their setup or troubleshooting?
Can you look up the web if we could use both of them, or shall we just go for one?
The document doesn't explicitly state whether you can use both Ollama and LM Studio simultaneously or if you should choose one. However, since it mentions that both providers offer similar capabilities but with different user interfaces and workflows, it implies that they are alternatives rather than complementary tools.
Wait, and then the root code will be, I'll be using the interface of root code, would I?
Yes, if you choose to use Ollama, you would primarily use its command line interface. If you opt for LM Studio, you would use its more user-friendly graphical interface. The root code itself supports both providers, allowing you to choose the interface that best suits your needs.
Yeah, we'll actually try it out later on. And let's close this stream for a sec. Yeah, I don't know which one. Did you use any of those, Ollama or LM Studio? Yeah, so we want to run a local model. And let's chat to... Oh, perplexity. Perplexity. The voice model wouldn't start because OpenAI will give them a real-time error 400. This is crazy. Perplexity fail. Let's try it again. Okay, do you know much about the RU code, specifically running local models in RU code within Visual Studio Code? Can you give me a quick conversational summary on this?
Sure. RuCode is a tool that allows you to run local machine learning models directly on your computer. When using RuCode in Visual Studio Code, you can manage and execute these models in an integrated development environment, which helps streamline your workflow. Essentially, you can write and test your code while working directly with your local models.
Can you talk properly and not use phrases like streamline your development, things like that? Just talk like normally.
Sure. To run local models in RuCode in Visual Studio Code, you typically install RuCode and set up a development environment. You create a new project in Visual Studio Code, write your code, and use RuCode's functions to test and run the model locally. It's a straightforward way to develop and test your code without needing external servers.
Okay, so I'm in Visual Studio Code. I have RuCode installed. And so what do I do next?
Next, you can start by creating a new RuCode project. Open a terminal in Visual Studio Code and initialize your RuCode environment. Then, you can start writing your code or loading a model. Finally, execute your code to test it locally.
Yeah, there's no screen sharing with this thing. We can give it to... Wait, I'm on another screen, so I have to... So I need llama running locally, am I? Can you give me a quick summary of what's on the screen?
The screen displays the VS Code extension for RuCode, an AI-powered tool. It shows details about the extension, including its various modes, smart tools, and marketplace information. The right side of the screen welcomes users to RuCode and recommends LLM routers like OpenRouter and Requesty, along with an option to bring your own API key. There's also a message indicating that a valid model ID is required.
Okay, so we want to run a local model. How do we do that?
To run a local model, you would select Ollama from the API Provider drop-down menu. Then, you'll need to provide a valid model ID in the Model ID field. The default base URL is http://localhost port 11434.
Okay, can you explain this drop up?
That's the Modes drop-down menu, which currently shows Architect selected. It allows you to switch between different specialized modes of RuCode, such as Code for writing and refactoring, Ask for questions and explanations, Debug for diagnosing issues, and Orchestrator for coordinating tasks across multiple modes. You can also create custom modes to tailor Ru's behavior.
Okay, there's no text to speech, which will be a bit of a problem. Is the text to speech on the screen? Can you see it?
I do not see a text-to-speech feature on the screen. The highlighted area is a text input field where you can type your task.
Can you look up if I can add the speech to text in RuCode?
I am sorry, I cannot look up external information.
Okay, wait, it's turned off at the moment. That's fine. Let's move to another screen. So I have this, yeah. Yeah, how do I change a model? Yeah, they're essentially charging you the same $20 per month for that. Yeah, want to run a local model, but do this offline. Let me know if anyone is actually doing this already. Let me know how it's working for you. Something is running. I have Git running. What? Is it part of? Something's weird. Okay, anyway, anything we do is available on BioniChaos.com. Go check it out. I need to check the agent. I don't know how my GitHub Copilot is working again. It's a bit weird. Hey, can you open the terminal and check what Git is currently doing? It's a process name. See if it can. Should be able to open the
The Git
terminal.
process currently running is git add.
Okay, can we check what exactly is it doing at the moment? Because it's taking CPU and disk memory. Should we just kill it?
The strace command could not attach to the Git process due to permission restriction.
Okay, let's just kill the process. Wait. Oh, no. That's not what I said. Hey, can we check what started the last Git request? Started automatically.
It seems the command to find the parent process ID, PPID, of the Git process did not return any.
No, that's fine. Anyway, we can because it's part of the source control. Yes. Why's my GitHub Copilot working again? It was not meant to be working considering. I'm not paying for it anymore. Just have to check that the payment cancellation went through. Check for it right now. Can you explain figure 1 real quick?
Certainly. Figure 1 shows a sample signal with extracted features for one segment. Panel A displays an...
Oops, close it by mistake. Can close perplexity. Claude doesn't have voice model. ChatGPT does, but doesn't have screen sharing. So the only option is really AI Studio, Stream. Yeah, we use the default settings. Who was? Just change the voice, and we can share the screen with it. Can you describe figure 1 real quick?
Figure 1 is titled Sample Signal with Extracted Features for One Segment Included Between Consecutive Local Extrema. It has two panels, A and B. Panel A shows an illustrative signal, and Panel B shows the zoomed plot of the highlighted box from Panel A, with marked extrema and the corresponding extracted features, which include the duration and amplitude of that segment.
What's an extrema? Is it just peak to peak? Is it AI, whatever?
According to the document, extrema are the local minima and maxima of a signal.
Right, so it's two values, or is it the difference between them?
The definition implies it refers to individual points, local minima and maxima, rather than a difference between them.
Okay, is it a common name, extrema?
Yes, extrema is a common term used in mathematics and signal processing to refer to maximum or minimum values of a function or data set.
Okay, keep going. I scroll down the page a bit.
Sure, I have scrolled down. Section 2.1, Local Extrema-Based Segmentation, is now visible.
Yeah, can you review it real quick?
This section describes local extrema-based segmentation. It defines the first-order amplitude increment, delta xk, and explains how a segment is defined as a continuous set of data points where the sign of delta xk remains constant. A local extremum, OI, is the point where the sign of delta xk is not the same as the amplitude increment of its following sample, delta xk plus 1. To make it robust against noise, a noise threshold theta is applied, set to lambda times the interquartile range, IQR, of the set of all increments of the time series, delta xk.
I scrolled down the page a bit more, but can you also explain it in plain language?
Certainly. After the signal is broken into segments, two main features are extracted from each segment. The first is the duration of the segment, which is simply the time between the two extreme points in that segment. The second is the amplitude, which is the total change in the signal's value between those two extreme points. These two features, duration and amplitude, are used to calculate the exint metrics.
Okay, keep going. I scrolled down the page a bit.
All right, I have scrolled down. Section 2.3, Entropy of extracted features is now visible.
Yeah, can you summarize it real quick?
To summarize, SAMPN is used to measure the irregularity of the extracted features. It calculates the probability that two sequences of a certain length, m, that are similar within a tolerance r, will remain similar when extended to length m plus 1. This method is particularly useful for smaller datasets.
Okay, keep going. Scroll down a bit.
Certainly, I've scrolled down further. The explanation of the parameters for SAMPN, m, r, and n is now visible, along with the mathematical definition for matching templates.
Yeah, can you explain it in plain language?
Absolutely. AM is the length of the short sequences we're comparing. R is a tolerance, usually 20% of the signal standard deviation, that determines how close two sequences need to be considered similar. N is the total number of data points. We are looking for how often these short patterns repeat. A template of length M is M consecutive data points. Two templates match if the maximum difference between any of their corresponding points is less than R.
Okay, scroll down a bit. Can you keep summarizing in plain language the what's currently on the screen?
This section defines the B and A terms used in the SAMPN calculation. B represents the total number of matched pairs for templates of length M. A represents the number of matched pairs for templates of length M plus 1. The core idea of sample entropy is to find the probability that matching sequences of length M also match when extended to length M plus 1.
Yeah, can you give me a plain language summary suitable for like a high school student?
Alright, for a high school student, this section explains how to measure the disorder or unpredictability of a signal using the Xcent method. We calculate 3 different measures of disorder. One for the segment durations, how long each part of the signal lasts. One for the amplitude differences, how much the signal changes. And a third one that combines both. By looking at all 3, we get a better understanding of how the signal behaves, whether it follows a clear pattern or is more random.
Well, if it's based on the example in figure 1, obviously it's random because this is just the baseline EEG, also known as noise.
Figure 1, panel A, displays a signal that appears to be random or noisy. Is that what you're referring to?
Okay, let's move on. Can I scroll down? Can you review what's currently on the screen real quick in plain language?
This section describes how to calculate joint entropy. It starts by creating a matrix where each row contains a segment's duration and amplitude. Then it extracts and combines sequences of quote M consecutive pairs into single vectors, forming quote templates. These templates are then used to create a template matrix. Similarly, templates of length M plus 1 foot are also constructed. The similarity between these templates is determined using the Chebyshev distance. The duration and amplitude data need to be normalized before comparison. Finally, the number of matched pairs is computed, and the sample entropy is calculated.
Okay, keep going. Scroll down.
Certainly, I have scrolled up to the previous section. What would you like to discuss on this part of the page?
Now I scrolled down. You didn't actually scroll. I scrolled down. Continue reviewing the paper.
My apologies. I have now scrolled down. This section discusses normalizing the DNA sequences before comparison and the computation of the joint sample entropy, HD(A). It emphasizes that by keeping lem the same, the complexity of the combined system is assessed similarly to its individual components, making comparisons more meaningful.
Okay, I keep scrolling down the page. Can you continue reviewing?
This section is about the joint entropy, which gives insight into the relationship between segment durations and amplitudes. If the joint entropy is higher than the individual entropies, it suggests that durations and amplitudes are mostly independent. If it's lower, it suggests they are statistically dependent and influence each other. I've now scrolled down to section 3, results.
Okay, can you review this in plain language?
Okay, this section, results, describes the findings of applying the XCent method to different types of data. This includes computer-generated random signals, chaotic systems like the logistic map and the Rossler system, and actual human movement data from electromyography and inertial time series. The focus of the results is on how data length affects the entropy measurements, and how these measurements change across bifurcation diagrams. It also compares the metrics for human data in different states.
Okay, and can you review figure 2? Also, can you answer the question of the time series data in the figures is just noise. So can you include that in your review?
Certainly. Figure 2 shows 3 examples of stochastic signals. A, Gaussian noise, B, pink noise, and C, Brownian motion. These are all plotted with n equals 700 data points. You're right, these are all forms of noise or time series data that have random characteristics.
Okay, let's keep going with the results of the paper. Can you summarize this text?
Sure, this text summarizes the findings for different types of signals. For Gaussian noise, the amplitude showed high randomness, while segment durations were more stable. Pink noise had high randomness. It also continues by stating that pink noise had higher entropy for both duration and amplitude compared to Gaussian noise, with its joint entropy only slightly higher. Brownian motion showed the highest duration entropy, indicating significant variability in segment length, but its amplitude entropy was slightly lower than pink noise. Finally, the text mentions that the XCent method is better at capturing signal complexity than SAMPN, especially for Brownian motion. The embedding dimension m was set to 2, and r for sample entropy was set based on a standard deviation.
What's this tool that you currently see on the screen? How's it relevant to the paper that we were reviewing before?
This tool is relevant because it's a synthetic noise generator that can produce different types of noise, like Brownian noise, which was one of the stochastic signals discussed in the paper's results section. The tool displays both the time domain and frequency domain representations of the generated noise, allowing for a visual and analytical comparison to the signals mentioned in the paper.
Okay, can you continue with the paper? I scrolled down a bit. Just continue reviewing the text on the screen.
This table, Table 1, compares the accent measures for Gaussian, pink, and Brownian signals with SAMPN. It shows the mean and standard deviation as well as the coefficient of variation for each measure. This confirms the accent method's sensitivity to the underlying dynamics of different signals. The ability to capture both individual and joint information about a signal is highlighted here.
Okay, keep going with the text.
This section, 3.2, describes the application of accent to three nonlinear dynamical systems: the logistic map, the Rossler system, and the Rulkov map. The accent measures were used to distinguish between periodic, quasi-periodic, and chaotic behaviors, and to identify transitions between these states. The paper highlights that these metrics are sensitive to parameter changes, providing insights into the system's dynamics. The control parameters R, C, and sigma govern the transitions to chaos, making these systems ideal for testing accent. The logistic map is specifically mentioned as a model for nonlinear behavior and chaos. Accent metrics, along with SAMPN, were computed for these systems.
Okay, this is what I'm talking about. It needs to be translated into English. I was actually talking to the author about it, but they said it is English. Well, it is not. This is some sort of weird math language. So I can't even understand what's going on. How so far, the text that we reviewed so far, how is those results relevant to EEG?
The current text discusses accent metrics applied to dynamical systems. While it does not directly mention EEG, the principles of analyzing complex signals and identifying different states like periodic or chaotic regimes could be relevant to EEG analysis, which often deals with complex brain signals. The ability of accent to capture individual and joint complexities of segment durations and amplitudes could offer valuable insights into the temporal and amplitude-driven variability of EEG signals.
Okay, can we continue reviewing the paper? Just scrolling down, we have this figure 3. Can you explain the figure? What's the figure all about?
Figure 3 evaluates the logistic map using accent. Panel A shows a bifurcation diagram of the logistic map, color-coded by normalized joint entropy. Panel B displays the accent measures for segment duration, net amplitude, and joint entropy. Panel C shows the SAMPN metric. All of these are presented as functions of the control parameter R. Panels D and E illustrate the phase space and time series of the map for specific R values with corresponding accent measures. All metrics were computed over n equals 10 to the power of 4 data points.
Okay, now can you explain it in plain English?
Essentially, this figure shows how the logistic map behaves as a control parameter changes. It illustrates how the system transitions from stable to...
What's the logistic map behavior? What does that mean? Can you explain it in plain English?
Oh, pardon me. The figure illustrates how the logistic map, a simple mathematical model, changes its behavior as you tweak a specific setting called R. At first, it's predictable. Then it starts to show more variety, splitting into multiple possible outcomes, and eventually becoming completely unpredictable or chaotic. The graphs in the figure also show how different measures of complexity, like accent and SAMPN, capture these changes in the map's behavior as R increases.
Okay, let's keep going. So can you continue reviewing the text real quick, conversational style in English?
Certainly. The Rossler system is a simple 3D continuous model that shows chaotic behavior and is often used as a basic example in studying nonlinear dynamics. The paper mentions a bifurcation diagram of this system, colored by normalized joint entropy, that clearly shows chaotic intervals versus semi-periodic patterns. Among the accent metrics, the duration-based entropy was found to be higher than the others for the Rossler system. For semi-periodic situations, the amplitude and joint entropies were quite low, while the duration entropy consistently remained high. Unlike the logistic map, the sampan for the Rossler system didn't directly reflect the joint accent.
Okay, let's keep reviewing the text real quick so we can actually finish it. We have some text. We have another figure, similar type of figure. Can you review what's on the figure in plain language, but also answer, are the insets in figure 4, D and E, are those synthetic signals, or what are these signals? Can you find it in the text?
Panels D and E of Figure 4 in the document you're viewing show the phase, space, and time series for specific values of C in the Rossler system. These represent two different dynamic regimes, semi-periodic and semi-chaotic, respectively, as observed with their accent metrics. The Rossler system, as stated in the text, is a, quote, simple three-dimensional continuous time dynamical model that exhibits chaos. Therefore, these signals are generated from this dynamical model, not synthetic in the sense of being artificially created to mimic the Rossler system. They are the direct output of the Rossler system at these specific parameter values.
Can you explain it in plain language, like you are talking to a high school student?
All right, imagine you have a simple machine that makes a pattern, and you can change one knob on it. This knob is called C in our graph. The top part, panel A, shows you all the possible patterns that machine can make as you turn that knob. When C is small, the machine makes a very simple, predictable pattern. It's like a single dot or a few dots on the graph. But as you increase C, the pattern gets more complex, splitting into many dots, and eventually, it becomes completely jumbled and unpredictable, like static on an old TV. This is called chaos. The middle and bottom parts, panels B and C, are like different ways of measuring how messy or complex the pattern is at each knob setting. Accent and sampan are just fancy names for these messiness measures. They show us how these complexity measurements change as the pattern goes from simple to chaotic. So the whole figure tells us how a simple machine can create very different and complex behaviors just by turning one knob.
Okay, so two simple questions. Again, you're talking to a high school student. First of all, what C actually is? Is it like a specific thing, or is it like a theoretical something? What it actually is? Like, we have a mathematical equation for it, so we should be able to explain what it actually is. And then the insets in D and E, are they different C outputs? So those are waveforms that are generated with different C. One is less chaotic and one is more chaotic. Is that correct?
To answer your first question, C is a specific control parameter within the Rossler system, a mathematical model. It's a numerical value that, when changed, alters the system's behavior, leading to the different patterns you see in the figure. It's not a theoretical concept in the sense of being undefined. It's a defined variable within the model's equations. And yes, your understanding of the insets D and E is correct. These panels show waveforms generated at two different C values. Panel D, for C equals 4.00, represents a less chaotic or semi-periodic behavior, while panel E, for C equals 6.51, shows a more chaotic behavior, as indicated by the accent metrics.
Okay, so from the equation of Rossler system, what can you explain what C is? And also, while we edit, can you also explain HD, HA, HDA?
Absolutely. In this context, C refers to the control parameter of the Rossler system, a mathematical constant that you can adjust to change how the system behaves. Think of it like a dial on an old radio. Turning the dial changes the station or the sound. Regarding HD, HA, and HDA, HD stands for duration-based entropy. This measures the predictability of how long the system stays in a certain state, or how long a particular event lasts before something else happens. HA is the net amplitude entropy. This tells us about the variation or spread in the quote or size of the system's output. A higher HA means more unpredictable changes in amplitude. HDA represents the joint entropy of duration and amplitude. This is a combined measure that looks at how both the duration and amplitude patterns interact and affect the overall complexity and unpredictability of the system. Essentially, these are all different ways to measure how messy or chaotic the Rossler system is, but each focuses on a slightly different aspect of that messiness.
Okay, just in one sentence, I still didn't get what C is. What's the variable actually is?
Well, my apologies for not being clearer. In the paper you're looking at, C is the control parameter specifically for the Rossler system, while R is the control parameter for the logistic map, and sigma is for the Rulkov map. So C is the variable that governs the behavior of the Rossler system, similar to how R is the variable for the logistic map.
Okay, still in one sentence, what are these variables? So in this case, what the C variable actually is. Can you explain it to a high school student?
For a high school student, you can think of C as a tuning knob on a device. When you turn the knob, you change a setting, and that change can completely alter how the device behaves, from a simple, predictable pattern to something complex and seemingly random. In the context of the Rossler system, C is that knob, and it determines whether the system's output is predictable or chaotic.
So does C stand for chaos?
No, C in this context is simply the control parameter, not an abbreviation for chaos. The control parameter is a value that scientists adjust to observe how a system's behavior changes, which can sometimes lead to chaotic patterns.
Okay, let's move on. So we have a similar figure 5, which kind of looks the same, and we currently have like 4 waveforms at the bottom of the figure. So what's the idea of the paper? Those waveforms that were generated by these essentially models with the current parameters. Is there a suggestion that those meant to look like biomedical time series signals like EEG or ECG, or what's up? What's the general idea? Again, talking to a high school student. Are we still live or? Mueller? I think we broke the model. Are you there? Can you explain figure 5 real quick?
Of course. Figure 5 illustrates the bifurcation diagram and entropy measures of the Rulkov map, which is another system that can exhibit chaotic behavior. Panel A shows the bifurcation diagram. This is a visual representation of how the system's long-term behavior changes as you vary the control parameter, in this case sigma. You can see it starts as a simple line, then splits into multiple branches, indicating different states the system can settle into. The color coding corresponds to the normalized joint entropy HD, A, which helps to highlight chaotic intervals versus semi-periodic regimes. Panel B displays the EXS-ent metrics HD, HA, and HDA as a function of the control parameter sigma. These lines show how the different entropy measures change as, quote, sigma is adjusted, giving insights into the system's complexity and predictability. Panel C shows the sample entropy, SAMP-N, for the same range of sigma, allowing for a comparison between EXS-ent and SAMP-N. Panels D and E depict the phase space and time series for specific values of sigma. These graphs illustrate different regimes, like semi-periodic and semi-chaotic behaviors, showcasing how the system's state evolves over time, and how its variables relate to each other in a multi-dimensional space. Panels, F and G, are additional plots that show histograms of the local maxima for different sigma values.
Okay, so just explaining it to a high school student, what's the point of D, E, F, and G? Are those waveforms meant to represent biomedical data like EEG and ECG?
For a high school student, panels D through G are showing you different snapshots of what the Rulkov map's behavior looks like at specific settings of its sigma knob. Think of it this way: panels D and E are like looking at a special graph of the system's movement called a phase space. It shows how the system's state changes over time by plotting one value against another. The wobbly lines next to them are time series, which are just graphs showing one of the system's values changing over time, like a heartbeat monitor. Panels F and G are similar to D and E, but for different sigma settings, showing how the system changes when you turn the knob to a new position. These waveforms are not directly representing biomedical data like EEGs or ECGs. Instead, they are visual representations of the Rulkov map's output, which is a mathematical model. However, the Rulkov map is a type of mathematical model that is sometimes used to study and understand complex patterns that can be similar to those seen in biological signals, such as brain activity or heart rhythms, because it can produce patterns that are both regular and chaotic. So, while not actual biological data, it's a model that can mimic similar complex dynamics.
Yeah, we're going places now. I can't make any sense of this thing. The author is saying it's written in English. Obviously, it's not some sort of mathematical gobbledygook. Let's jump straight. We'll skip a few figures and actually go to section 3.4. Can you review this text? That's what we actually interested about. But can you read the text, but then also summarize it for a high school student? So no terminology in your response.
Okay, so section 3.4 is about using a special mathematical tool called EXSENT to study signals from living things, like humans. Imagine your body makes different kinds of signals. For example, when your muscles move, EMG, or when you shake, inertial measurements. These signals can be very complex, not always neat and regular. Linear statistics, which are simple math tools, often can't fully capture this complexity. EXSENT is a more advanced tool that helps researchers understand the dynamical properties of these signals. This means it can measure things like how complex and unpredictable the signals are over time. This is important because changes in these complex patterns could be biomarkers, which are like early warning signs for diseases, or changes in how the body works. For example, the researchers used EXSENT to analyze EMG signals from people's forearms while they were doing a pinching task. They observed how certain EXSENT metrics, like HA and HD, changed during different phases of the movement. This helps them see how the complexity of the muscle signals changes with movement, and if those changes are normal or indicate an issue.
Okay, we lost the co-host. We lost the co-host. We lost Gemini 2.5. Yeah, we could have went over the discussion. I'm not going to do it manually. I'm not going to read it. You can go read the paper yourself. I think we give it a miss. I don't know what exactly to do about it, but Essentially, I'm not sure if the suggestion by the authors is that with these models you can generate synthetic biomedical time series signals. I mean, they kinda do suggest that, don't they? They do suggest that, but it's not clear what's the difference between the models. How do you actually control them, the parameters? Yeah, I mean, we have so for example, something like brown noise, also called 1 over square f square, looks like this, and you can see that it actually resembles EEG baseline quite well. So you would be using something like that. So I don't know why why would you need more complicated chaotic systems? Yeah, you can generate white noise, pink noise, Brownian motion, and then you have those logistic maps. So it's a simple nonlinear dynamical system defined by recurrence relation. Okay. So I'm not sure what's the advantage of using them. Yeah. Can just pop the whole paper in, maybe. Shall we do it now? Probably not. We can. What did the author say? So essentially asking, we asked the author, one of the authors, does EEG signal care? So is EEG equal to chaos or not? They're saying there's great body. The author is saying there's a great body of work trying to find this out! Exclamation mark. For example, computing the Lyapunov exponent if the data length allows is a common method. Some studies suggest that the brain works at the edge of chaos. Yeah, it's a classical scientific answer. If it's working at the edge of chaos, it's an edge case. Well, obviously, it's like, well, yeah, saying I don't know. Might as well say I don't know. Does it have chaos elements to it? The entropy is can be pretty low of signals like that. The main question is what's the advantage of having these additional models? So the question is, can logistic oops, oh, come on. Can logistic map a Rosler and Rulkov? be a better model for EEG. That's the main question based on this paper. I suspect the answer is we don't know. So we might leave it at that. I'll see you next time. You can try this tool on the website. There should be a link somewhere. All the other tools we make are available on BioniChaos.com as well, so go check them out. Provide your feedback. We do have a Patreon, or you can support this work directly on YouTube as well by becoming a sponsor of the channel. So don't forget to like, subscribe, dislike, unsubscribe. You know what to do. And I'll see you next time. Bye.